Hello everybody from Math 2200, it's Discrete Mathematics. It's Professor Wenson here again with a video on your ZyBooks Section 8.2 titled Recurrence Relations. Recurrence relation is another way to define a sequence. You saw in Section 8.1 how to define a sequence with an explicit formula. Right, where you could just plug in the index, plug in your input, and know what the term was without having to know previous terms. Well, in a recurrence relation, these are sequences that are defined implicitly, not explicitly. So that means you're going to have to, in order to find one term, you'll have to know what the values of previous terms are. You'll see what I mean when we get to some of them. So, some sequences are most naturally defined by specifying one or more initial terms and then giving a rule for determining subsequent terms from earlier terms in the sequence. So a rule that defines a term, a sub n, as a function of previous terms in the sequence is called a recurrence relation. For example, in an arithmetic sequence that you saw in section 8.1, each number is obtained by adding a fixed value, right, that common difference, to the previous number. So a way to define an arithmetic sequence, using a recurrence relation, I state the initial value, and then a formula where the nth term is a function of the n minus first term. Right, the value when if I want a sub n, I take a sub n minus 1, right, the previous term, and then add d. Right, and this is for starting with index 1. Right, and this is the way every recurrence relation will look. You'll have some initial value or values stated, and then you'll have a formula showing you how to get one term by using previous terms. And the same thing goes for geometric sequences, right? If I state the initial value, and then remember how in a geometric sequence every term was the previous term times some common ratio times some r. So a sub n equals a sub n minus 1 times r. That's just every term is the previous term, that's what this n minus 1 is, times r. And this is for indices 1 and beyond, right? Because you're given when the index is 0, and then from 1 and beyond you follow this rule. A very famous example of a recurrence relation is the definition of a Fibonacci sequence. Leonardo of Pisa, Leonardo Fibonacci. Talking about rabbits multiplying and all that. So you see here some initial terms are defined, and they go through here and show you how this works. I'll do it on some paper though. All right. So here's a Fibonacci sequence. So again, we're given some initial terms. Now notice this one has 2 of them. And every single recurrence relation will be like this. You're going to have an initial term or multiple initial terms stated. And then you have your rule showing you how to get future terms. Terms when the index, we have when the index is 0, we have when the index is 1 what the term is, and then the rule for how to find terms when the index is 2 or greater. So, when n equals 2, right, when n equals 2, starting at the index of 2, we have f sub 2 would be equal to f sub 1, right, see 2 minus 1, plus f sub 0, right, 2 minus 2, just replace them with 2 everywhere. And all this rule is stating is that every term is the previous term plus the term before that. So every term is the sum of the previous two terms, right? If you're at the nth term, n minus 1 would just be 1 before it, and then n minus 2 would be 1 before that. And that's what we're seeing here, right? So this f sub 2 would be f1, which we're given, one of these initial terms was 1, plus f0 is 0. So the value of f2, this term, is 1. And then I can do this for every value, every index 2 or greater. So for n equals 3, f3, and just go through the rule and replace n with 3. So f sub 3 would be equal to f sub 3 minus 1, so f sub 2, which is the previous term, plus f sub 3 minus 2 is 1, which is the term before that. F sub 2 we just found was 1, plus f sub 1 was given, was also 1, that's 2. Alright, so the the fourth term in the sequence with this index of 3, f3 is 2. And I'll do this one more time here. So for n equals 4, to get the fifth term, f sub 4 here, just go through the rule, replace all the n's with 4. So f sub 4 minus 1, so f sub 3, plus, and then f sub 4 minus 2, f sub 2. So the fourth term, or I'm sorry, this f sub 4 is the previous term plus the term before that. So f3 we found was 2, and f2 we found was 1 from this line. And 2 plus 1 is 3. And I can do this forever. All right. In fact, I'll start writing this terms of the sequence in a list up here. So we had 0 for the first term, then 1, and then 1 plus 0, 1 plus 1, 2 plus 1, 3 plus 2, right? So f5 would be 5, and then 5 plus 3, then 8 plus 5, then 13 plus 8, then 21 plus 13, and so on. Like I said, I could do this forever, but every single term is the sum of the two terms before it, and that's exactly what this rule is stating. So this is an example of a Fibonacci sequence. Okay, and they go through that in the animation here if you want to watch that step by step like I did. All right, so let's take a look at this, and I'll write out the first several terms of this sequence defined recursively. Again, it's recursive because you're given some initial term or terms, and then you have a rule where one term depends on previous terms, right? I can't just find the 100th term right away. Back in the Fibonacci sequence here, if I said, find f100, that would take a while. Because right now I'm at 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Right now, this 34 is f9. I'd have to go and do this until I got to f100, right? I can't just plug 100 in and know what the term is. So that's the one drawback of a recursive formula, recursive relation. Now, we can solve a recursive relation, and we're going to see how to do that later in this chapter, not in this section, but in a later chapter. You can solve a recurrence relation and figure out, an explicit formula for the sequence, and then I could plug in 100 to that and figure it out. But for right now, we're only getting these recursive definitions. All right, so I'm going to write this down on some paper, come back, we'll look at the first several terms of this sequence. So again, here we're given some initial terms, right? So the first two terms of this sequence are 1 and 1, right? That's b0 and b1 that we're given there. I can find the next term by, using this rule. And this is for, when n is 2 or greater. So I'll first look at when n is 2. I'll plug in 2 for n. So just go through this rule here, plugging in 2 for n. So I have b2, the next term, is going to be b sub 2 minus 1, so b sub 1, times b sub 2 minus 2, which is b sub 0, and then plus 2. So what this is saying, all this rule says, is that every term in this sequence is the product of the previous two terms, right? n minus 1, n minus 2. It's the product of the previous two terms and then plus 2. Well, what were the previous two terms here? So b2 is b1 times b0. So b1 was 1, b0 was 1. So that's 1 times 1 and then plus 2 after. 1 times 1 is 1, plus 2 is 3. So the next term in this sequence is 3. Then I'll go look at when n is 3 for the next term. All right, so we have b sub 3 equals, b sub 3 minus 1, so b sub 2, times b sub 3 minus 2, so b sub 1, plus 2. And then what's b2? That was 3, times b1 was given to us, that was 1, and then plus 2. 3 times 1 is 3, plus 2 is 5. All right, so the next term in this sequence is 5. I'll do one more. N equals 4. Just go through the rule here, replace all the n's you see with 4. So b sub 4, which is again the fifth term, because we start with 0. The fifth term here, b sub 4, would be b sub 3 times b sub 2 plus 2. So b3 was 5 times b2 we saw was 3 plus 2. So this is 15 plus 2, that's 17. Alright, so that's the next term of the sequence. Now, again, you could also just think, you could do this pretty quickly. So remember the description. Every term is the product of the previous two plus 2. So the next term will be, 17 times 5, which will be 50 plus 35, that'll be 85, plus 2, 87, and then I don't want to do the next one, right? Because that'd be 87 times, I could use a calculator, but or do it by hand. I mean, it wouldn't be that hard to do it by hand, but 87 times 17, whatever that is, plus 2 will be the next term, and so on. Okay? And again, you can do this forever. And then you can see how painful it would be if I asked, well, what is B1000? You wouldn't want to do this 1,000 times. But we would have to, because I don't have an explicit formula where I can just plug in 1,000 and know what the term is. If I want to know B1000, I need to know B999 and B998. Again, we're stuck with, for now, we're stuck with these recursive definitions. So what is B2? I already wrote out what that was, so you can type those in if you want. Alright, the challenge activity. You're given a definition of a sequence called Fn here, whose domain is a set of all non-negative integers. So non-negative means, 0 or greater. So starting at 0, notice they give us f sub 0 here. So f of 0 is 5. First term of the sequence is 5. And look at the rule. So again, I'll write this out on paper. And let's look at the first several terms of the sequence. So here we have, f of 0, f sub 0, f of 0 is 5. And then for one or subscripts of 1 and greater, inputs of 1 or greater, fn, f of n is equal to f of n minus 1 plus 3 times n. Alright, and this is for n greater than or equal to 1. Alright, so let's see what, so again, all this is telling me is that fn, every term is the value of the previous term plus 3 times the term number I'm at, or the index number I'm at. So again, just go through this rule, replace n with 1. We'll start with 1. So f1, f of 1 will be equal to f of 0, right, 1 minus 1, plus 3 times 1. Replacing again n with 1 here. So f0 we saw was 5, right, and then 5 plus 3 times 1 is 8. So our first term is 5, this f0. Our second term is f1, that's 8. Then plug in n equals 2. And we get f2. When n equals 2 in this rule would be f sub 1 plus 3 times 2. And again, replacing n with 2. So this is f1. f1 we saw was 8 plus, 3 times 2 is 6. 8 plus 6 is 14. So the next term is 14. And then I'll do one more. N equals 3. So again, just go through the rule. Replace all the n's with 3. f3 would be equal to f2 plus 3 times 3. So 14 plus 9, or 23. And again, I could do that all day long. I could do that forever. And then back here, in the challenge, they wanted f2. They wanted that third term, which was 14. Okay, and then I think all 4 of these will be pretty similar. Yeah, so here's another rule. Again, just pay attention to how the rule is defined, and hopefully you're using it properly. Yeah, the fourth level. Now notice how the fourth level, the rule, to get one term, I need to know the previous 2, right? N minus 1, n minus 2. And they want you to go all the way out to f5. Right, f5, the 6th term. The first term is at 0, so f5 is the 6th term of the sequence. All right. Now here, the number of initial values required to define a sequence using a recurrence relation depends on which previous terms in the sequence are used to define the nth term. Like if you have to go back to the 2 terms, you need to be given 2 terms. Like here and back in the this here. If I have to go back to n minus 2, if I have to go back 2 terms, I need to be given 2 initial terms. Same thing for the Fibonacci sequence. If I have to go back 3 terms, I need to be given 3 initial terms. So that's what this is all saying. So each question below gives a recurrence relation. How many initial values must be given for the sequence to be well defined for all n greater than or equal to 0? So again, you see here, they're saying Cn equals 3 times Cn minus 1, that's the previous term, plus 2 times Cn minus 2, that's 2 terms prior. 2 terms prior, so I need 2 values given to me. Same thing here, this goes back 2 terms prior, dn minus 2. This one, however, bn equals bn minus 3 times bn minus 2. See how this bn minus 3 goes back 3 terms. So I need to be given 3 initial values to be able to define this sequence. All right, so look at the subscripts. They define a dynamical system here. It's just a system that changes over time. We can this whole thing here is that you can just define a dynamical system, one state after the other, in a recursive way using a recursive definition. And you can read this example if you wish. I'll just go over one of these participation activities. So here, each question describes a dynamical system and the corresponding sequence. Select the recurrence relation that describes the sequence. All right, so here it says, let Sn be the salary of an employee in year n. So n is the year number. The employee receives, a $1,000 bonus in December. The salary for the next year is 5% more than the income received by the employee in the previous year, including salary and bonus. So, which one of these rules describes this situation? So, remember they said the salary for the next year is 5% more than the income received in the previous year, including the bonus. So let's see what this first rule says. SN, so the salary in year N, is 1.05, 105% of the salary in year N minus 1. So this is 5% more than the previous year's salary, and then they add the bonus. That is not what's described here. This is 150%, so no way. They said 5% more, not 50% more. So it's got to be this one, right? See 1.05. The salary in year N is 1.05, 5% more than the salary last year, year N minus 1 plus 1,000. And you see how they did that in parentheses. See, they added the bonus to it first and then added the 5% more. That's exactly what's being described up here. So just pay attention to how this is worded, and I'll let you look at the second one. All right, and then you have additional exercises. Again, I've assigned, I don't remember if I think I assigned all of these. I don't recall. Some of these may be on chapter 8, assignment 8. Some might not be. Even if they're not, I would still recommend doing them all, just to get more practice, more exposure to the material, right? You get better at it that way. And of course, you can look at the solutions, check yourself. Please try to work them out. Try to, figure out what you're doing before you look at the solutions. Don't just copy down solutions. You're not going to learn anything that way. And of course, if you have any questions, let me know. And thank you very much for watching.